Hello and welcome to this Dr. Frost's maths video on Key Stage 5 graphs of exponential functions. Now if you've done a qualification like say the GCSE, then you'll be familiar with what a basic exponential function looks like. So an exponential term is something of the form a constant to the power of x. So that could be, for example, 2 to the power of x. And if we were to just try and plot some values, so let's just say that we actually had y is 2 to the power of x, and we had different values, so -3, -2, -1, 0, 1, 2. Then 2 to the power of -3 is an eighth, 2 to the power of -2 is a quarter, 2 to the power of -1 is half, 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, etc. And if we were to draw this, then if we plot the 1 here, so 2 to the power of 0 is 1, that's the y-intercept. Then an eighth would be sort of about here, quarter would be here, half would be here. We've got 1, 2, 4, and it's going up rapidly. So it kind of forms a shape like this, a kind of aeroplane taking off. So that's what y equals 2 to the x looks like. But he wants us to draw 2 to the x and 3 to the x on the same axis. So if I just draw that again, so let's say our 2 to the x is here. We should always draw on any intercepts of the axis, so it's going to be 1. What happens if we draw y equals 3 to the power of x? Well, note that 3 to the power of 0 is still 1, so we still get the same point here. Now, compare 2 to the 1 and 3 to the 1. 2 to the 1 would just be 2, but 3 to the 1 would be 3, so it would be slightly higher. So, 3 to the x is going to go up more rapidly, but compare 2 to the power of -1 with 3 to the power of -1. 2 to the power of -1 is half, but 3 to the power of -1 is a third, which would be smaller. So it's actually going to be underneath this curve for negative values. So that is a sketch of y equals 3 to the x. So for positive values of x, it's greater. For 0, it's the same. And for negative values of x, it's actually going to be lower. Now question 2, we've got some transformations here. So we want to sketch e to the x and e to the x plus 3. Now we kind of look at e to the x in other videos, but basically e is just a constant. It's known as Euler's number, and its value is approximately 2.71. It's certainly that to 2 decimal places. So it's just ultimately an exponential function, just like all the others. It's going to look like this. But how would we draw y equals e to the x plus 3? Now we've got to think about function transformations. Can you see that plus 3 is inside the function? If, say, f of x was equal to e to the x, then what would give us e to the x plus 3? Well, we've replaced x with x plus 3, so this is f of x plus 3. So we can see that the change occurred inside the function. That plus 3 was inside the exponential function. And do you remember that we do the opposite, and it affects the x-axis if that change was inside the function. So the opposite of plus 3 is -3. We subtract 3 from each of the x values. So it's basically going to shift 3 to the left like this. It's shifting left, translating left by 3. So that's y equals e to the x plus 3. But the one thing we're missing is the y-intercept. So if x was equal to 0, we get this y-intercept. E to the power of 0 plus 3 is e cubed, isn't it? So this y-intercept here would be e cubed. Now question 3, some more graph transformations. So we want to sketch y equals 2e to the x plus 1. Now when we sketch 2e to the x, that 2 is outside of the exponential function, so it's going to affect the y values and does what we expect. So the y values are going to be doubled. So if that's e to the x, then 2e to the x, it will go through 2 instead of 1 because all the y values are doubling, and it will just basically be steeper. But it's kind of quite hard to see it because we haven't put a scale on the x and y axis. These are only sketches, not plots. But that plus 1 is also outside the exponential function and now have the effect of adding 1 to the y values. It's outside the function, so it affects the y values, does what you expect. We add 1 to the y values. So the whole graph, this whole graph will be shifted up, translated up 1. Now can you see that on the original e to the x graph, we have this asymptote here, because this curve is approaching this straight line, y equals 0. Now that asymptote is going to get translated up 1. So now we've got an asymptote and we have to give the equation of the asymptote y equals 1. That 2 doesn't affect the asymptote, by the way, because if the asymptote was originally at y equals 0, then doubling that is still y equals 0. 0 times 2 is still 0. But the add 1 shifts that asymptote up 1, and now this curve is going to be sort of hovering above this new asymptote. That whole thing has been shifted up 1. Now we do need to give this new y-intercept, so if we make x 0, 2 to the power of 0, 2 times e to the power of 0 plus 1 is equal to 2 plus 1. So this y value, this y-intercept here, is going to be 3. What about b? Y equals minus e to the x. Now this minus is outside of the exponential function, so it's going to affect the y values and do what we expect, so it's going to negate the y values. So that's just going to flip it upside down, because all the y values are going to be negated to end up down here rather than up here. So instead of like this, it's actually going to flip it upside down. It'll be like that instead. And we need this y-intercept. If we had minus e to the power of 0, then that'll be minus 1. So that y value will be 1. Let's do these harder graph transformations ones. We got y equals 3 minus e to the x. Now I suggest doing this in bits. We know what y equals minus e to the x looks like. It looks like this. And then this is minus e to the x plus 3, if we just write this the other way around. So that's going to translate the graph up 3. So this asymptote here, which is currently the x-axis, is going to go up 3. So we now have an asymptote at y equals 3. And then let's consider the y-intercept as well, because I don't know if this is going to cross above the x-axis or below the x-axis. If x was 0, then we get y equals 3 minus e to the 0, which is 3 minus 1, which is 2. So this crosses at 2, and then it's going to have this shape here. Now we could also work out what this x-intercept is, but you don't know how to solve exponential equations yet, so we'll cover that in another video. And finally, we've got d, we've got y equals e to the 3x. Now this one's quite hard to draw, but I'm going to compare it to an e to the x graph, so you can see the difference. Now that changes inside the function, the times by 3, so it affects the x-axis, does the reverse, so we're going to divide the x values by 3. So this value here, we're dividing the x value by 3, it's now going to be here. This point here, we're dividing the x value by 3, it's going to end up here. This x value 0, we divide by 3, it stays where it is. This x value divided by 3, it ends up here. So we're going to see this new graph is going to look basically like this. It's a stretch parallel to the x-axis by a scale factor of 1/3. That's the way we could describe it. Now we've got some new types of graph. These are all examples of exponential growth graphs because we can see it's growing. As x increases, y increases. We've got exponential growth. It's called exponential growth because it's an exponential term. But these ones are examples of exponential decay, and it's basically where we have a negative power on your exponential term. So if we sketch y equals e to the x, the best way of thinking about this is as a graph transformation. We can see that we've negated the x value, so it does the opposite and affects the x-axis. We're going to negate the x values. So instead of doing like this, it's actually going to go the other way. So we end up with a graph like this. The y-intercept is still 1 because when we reflect this e to the x graph, flip it over, that y-intercept stays where it is. So this is known as an exponential decay graph. Decay just means decreasing. Just like you get radioactive decay, it's when a radioactive material becomes gradually less radioactive. And then what about this one? We've got y is equal to 10 minus 5 e to the minus x. This is quite a complicated one. Well, let's do it bit by bit. If that is an e to the minus x graph, then a minus e to the minus x graph will be this one flipped, so we end up with this. And then if we times it by 5, it's a stretch parallel to the y-axis of scale factor 5, but because it's just a sketch, not a plot, it's not going to look much different without any scale. And then we're adding 10 to the y value, so it's going to shift it up 10. So this is going to become an asymptote at 10, because the asymptote was at y equals 0, the x-axis, and now it's up here. and it's basically going to do this, isn't it? Now I'm not going to work out the x-intercept, but I am going to work out the y-intercept. If you make x 0, you get 10 minus 5e to the 0. That's 10 minus 5 times 1. 10 minus 5 is 5. So it looks like this. And then question 5, and then we've got a few questions after it on exponential modelling in real life context. Describe the transformation from y equals 2x to 2 to the x plus 3 using a translation and using a stretch. So we're going from y equals 2 to the x to y equals 2 to the x plus 3. Well, one way of looking at it is that the input of the function, this x, we've added 3 to it. So that's a change inside the function. So it's going to do the opposite and affect the x values. So that's going to be a translation left 3. You're subtracting 3 from the x values. So we could write a translation by minus 3, 0. So that's just going to move left 3, isn't it? But how could we describe this as a stretch? Well, the clever way of doing this is to realise that 2 to the x plus 3, using laws of indices, could be written as 2 to the x times 2 to the 3, which is 8 times 2 to the x. And can you see that to get from this 2 to the x to 8 times 2 to the x, well, we've multiplied it by 8 outside of this exponential function. So that's going to be a stretch parallel to the this by scale factor 8. And it's just really interesting that actually we could see this particular transformation in 2 different ways, as either as a translation or as a stretch. Now to finish off with, we're going to do some exponential modelling using these graphs. So let's read these questions. The population P of the Republic of Dave, well done if you've managed to get that very obscure reference. T years after 2000 is modelled by the equation P is equal to 100 times e to the 3t. Interpret the meaning of the 100. Well, can you see that if I was to make t equal to 0, that's when 0 years have elapsed, so that's a starting time. Then we would have 100 times e to the power of 0, and e to the power of 0 is just 1, so we just end up with 100. So it seems that the 100 there on the front is the value we would get if t was 0. And we call that the initial value. 100 is the initial population, i.e. when the time is 0. What is the initial rate of population growth? Now we've seen in a different video how we differentiate exponential terms like this. But basically, when you differentiate e to the power of kx, you get k e to the kx. And this is something using called the chain rule, but you don't need to know the chain rule yet. You just need to appreciate for the moment that when we differentiate an exponential term where e is the base, we just times it by whatever number's in front of the variable. So in this case, if we differentiate p with respect to t, because it's in terms of t, then we just need to times by that 3, and that 100 will become 300 e to the 3t. So it's saying, what is the initial rate of population growth? Well, the initial rate is when the time is 0. So when t is 0, that gives us that dp over dt is 300 times e to the 0, which is equal to 300. And if we want a unit for that, the rate of population growth is people per year, because t is in years here. And then C, estimate the year in which the population will reach 200 million. So we need this population, this, to be equal to 200 million. So 100 e to the 3t is equal to 20 million, sorry, not 200 million. So we need to solve this equation. Well, we've got this 100 in front of the exponential term, so let's just divide by 100. So e to the 3t is now equal to 200,000. And then somehow we need to get rid of that e to the power of in front of 3t. Now we'll see in another video in solving exponential equations that to get rid of the e to the power of, we do the inverse of it, which is the natural log. And that's actually the ln on your calculator. So if we do the natural log of both sides, the natural log of e to the power of 3t will get rid of that e to the power of, leaving just 3t. And then the natural log of 200,000, sorry, I accidentally wrote 2 million, is something we'll work out in a second. And then we just divide both sides by 3, so it's a third ln 200,000. And we get 4.0 4.07 years. So it will take 4.07 years in order for the population of the Republic of Dave to reach 20 million. So it's going up very rapidly. And then we've got this final question here. The share price of Frost Inc. P in pounds T days after launch is modelled by this equation, P equals 2000 plus 1000 e to the minus 1.1 t. So this is an exponential decay graph because we have a negative number in front of that variable in the power of the exponential term. So what is the initial share price? So remember, the initial value means when t is equal to 0. So for A, we just make t 0. And we get P is equal to 2000 plus 1000 times e to the 0, which is just 1000 times 1, which is 1000, and that is equal to 3000. So that's the initial share price in pounds. Then we want to actually sketch this. Now we did something similar to this earlier. We know an exponential decay graph looks like this. It's like a plane landing rather than a plane taking off. Timesing it by 1000 is just going to stretch the y values, but it's not going to look different in shape. But we're adding 2000, so it's going to shift up by 2000. So now we've got this asymptote of p is equal to 2000, and then it's going to hover just above like this. So this is what the shape is going to look like. And we can't actually have negative time, so it's just going to be this bit here. We don't actually want that bit of the graph. So it starts at some positive value and gradually decreases tending towards this value here, which is going to be relevant for the last part of the question. Then C, after how many days will P be £2010? So here we want the share price P to be equal to 2010. So we just make that equal to this expression for P here, the share price. And then we just have to solve it. So if we minus 2000, we get 10 is equal to 1000 e to the minus 1.1 t. Then we don't want this 1000 in front of the exponential term, so we divide both sides by 1000. 10 divided by 1000 is 0.01. Now we want to get rid of this e to the power of in front of the minus 1.1 t, so we again natural log both sides. So we do ln of 0.01. And when we do ln of this, the natural log of this, it gets rid of the e to the power of, giving minus 1.1 t. And then we just divide both sides by minus 1.1. So we get ln of 0.01 over minus 1.1. And if you put that in a calculator, you get 4.19. And what unit is this? It's after how many days? So this is going to be in days. And then finally, what is the long-term share price? Now, what the long-term value is basically as t gradually increases, getting really big, so a lot of time has passed, what will be the share price? Now, we can see this directly by observation from our graph. We can see as the time becomes large in the long term, we can see that the share price is approaching 2000. So we can just get directly by observation that the share price is going to be 2000. But if we didn't have this graph, we could find it just by putting a really large value of t, i.e. a long amount of time has passed, a long term, into our original equation. So let's just say, I don't know, t was 1000. If I do 2000 plus 1000 times e to the power of minus 1.1 times 1000, or just any really big number, and the calculator just gives you 2000. Because this term becomes so small that effectively we're just left with the 2000.